We are on to the last stretch here, and I want to talk to you about, I'll continue a bit about entanglement in the first half, and then we'll switch to some other things. So, where we had sort of motivated why we might find some simple geometric expression for entanglement entropy in holography, and I motivated for you chronologically the story of ER equals EPR, and then the earlier work of Takanagi and the HRT of trying to come up with a prescription to compute holographic entanglement entropy. So let me give you the prescription, and let's try to compute it in some simple cases. So given some region A on the boundary, which lives on a constant at some constant time slot, we are instructed to find generally a minimal an extremal surface which is anchored on this entangling surface dA. So the picture we drew yesterday is that we have this extremal surface, and this is A. It's important that what you're solving for is, you should think of this as like trying to solve a soap bubble problem. You have A is some region, but what really matters is its boundary, the entangling surface dA. So that's like the wireframe that you have for a soap bubble. So if you dip some wireframe inside a soap solution, the wireframe is dA, and then the soap bubble that extends out of the wireframe is this extremal surface. And the fact that this extremal surface is not a soap bubble in flat space, but it's in a soap bubble in some gravitational background, is what makes this interesting. It's sort of non-trivial. So how do we find EA? And the entanglement entropy itself is given by the area of EA in units in Planck units. To find EA, you can do two things which are equivalent. You extremize the area functional, and the way you do this is, let's say we bulk coordinates are xm, which is the set z and x mu, and some coordinates, we can pick some random coordinates on EA. Then the induced metric is just obtained by pulling back the metric from the space-time onto the surface, and you extremize this action you find solution to the Euler-Lagrange equations. From the minimal surface action, we'll just call it extremal surface action. Which is the Nambu-Goto action for this surface. Okay. The difference from the Nambu-Goto problem is that this is a higher dimensional surface, it's not two-dimensional. Just remember that EA is codimension 2. In space-time. So that's the sort of algorithmic way. You just write down some coordinates, extremize, you get some, generically you'll get some partial differential equations. You have to solve them subject to the fact the Euler-Lagrange PDEs should be solved with boundary conditions that boundary of EA on boundary of M is the boundary of A, and EA is smooth. Okay. So that's those are the boundary conditions that you want to solve for. So you can go ahead and try to solve PDEs. I won't solve PDEs for you. If you want to know how to solve the PDEs in some nice examples, ask Eric, who knows how to do them very nicely. The other class of other formulation of the same problem, a reformulation of this problem, which sometimes is useful for some conceptual things, is to realize that EA is codimension 2. It means that it has two normal vectors, and the local normal bundle has Minkowski signature, is a copy of R11. So as I said, so this is EA is a space-like surface, so it's sitting in a space-time. So one direction away from that surface is time-like, the other direction is space-like. So that's what this statement means. It means that so let's pick the normals, adapt normals to null coordinates. Let me take the normals to be N1, we call them N1A, N1M, and N2M, with N1.N2 equals -1, N1.N1 equals 0. I can always do this if I have two vectors, which are one of which is space-like, one of which is time-like. I can recombine them into two null vectors and go to some light cone-like coordinates. And you can define an extrinsic curvatures by taking the covariant derivative of these vectors in space-time, and extremality, you can convince yourself, is equivalent to I've written this covariantly, but you really should project these guys onto the surface and then take the trace. Okay. So basically, what this says is that this surface is sitting in some ambient space-time. It has two directions away from it. It's like the stick, which is one-dimensional in three-dimensional space, and if you sort of if you ask how it is bent in this direction and in this direction, it has some bending, which is what the extrinsic curvatures measure, and the bending is such that there's no trace to the bending. So the local mean curvature is 0. That's that expression, but you don't have to go through this differential geometric construction. You could just solve the surface problem this way. Okay. Is that clear? So that sets up the algorithm. So it's a very clean geometric problem to find EA. And once you find EA, you have to plug it back into that area formula, evaluate its area, and you have to do some regulating to make sure that you get the right answer as you go to the boundary of ADS in some regulation scheme. But apart from that, it's very straightforward. So the complicated path integral that we had to do for trying to compute entanglement entropy in field theory, and then compute all the Rennies and take analytic continuation to away from integers to get the entanglement entropy, is all distilled into finding some simple bubble problem in some geometry. Okay. So let's do a calculation. Let's do a couple of calculations just to see what this predicts. And I'll just use the I'll just work out the answer using this area functional. So my first example is going to be a two-dimensional CFT on Minkowski space. And I'll take the state to be the vacuum. So I need to tell you all this because the answer for the entanglement entropy cares about what state I put my field theory in and on what region I pick. So this tells me what field theory, this tells me what state, and let's take the region to be some interval. It's a spatial interval which goes from minus L to L. Okay, so here's our problem. So this is boundary x runs from minus L to L. Time is suppressed. This is x. This is z. So you translate the first statement that I'm talking about, the CFT in R11 and the state being the vacuum, tells me that the dual geometry is ADS3 in Poincare coordinates. So I can write down the metric. And this state is time independent, it doesn't evolve. So we can go back and just use the Kanagi formula. But the point is simply what we want to find, the extremal surface is a codimension 2 surface in a 3-dimensional space-time, which means it's a 1-dimensional curve. is a curve, is an extremal curve, which extremizes its length, and has is a space-like curve that extremizes its length, which is a space-like geodesic. Okay. So because d by dt is killing, and orthogonal to surfaces of constant x and t, of x and z, what it amounts to is saying that you can find a curve in the xz plane. In other words, we have a curve that could have in principle moved in time, z and x, but because of the symmetries of the problem, moving in time gives you an extra penalty, so you don't want, the curve doesn't really want to move in time, so you can just look at a constant time slice and solve the problem in a constant time slice. But you can convince yourself by just trying to compute geodesics explicitly in this three-dimensional space-time and seeing what you get. So in my notation, the induced metric, so if I pick some coordinate c on the curve, then the induced metric is x prime dc squared, and so you just have to solve the resulting ODEs that come out of this one-dimensional geodesic problem, and well, it's reasonably straightforward. So here's the solution. And the length, the area, is given by, if you plug this solution back in, which gives you an answer which is so what's really happening is that the curve is really a semicircle in this geometry. Bad semicircle. Okay. And in computing the answer for the integral, I have cut off the z integral at some z equals epsilon. whereas the true boundary is at z equals 0. Is that clear? So we can use some facts. If I translate this Newton's constant to the central charge of the two-dimensional CFT, the correct translation is this. This is a formula that goes back much before ADS CFT to work of Brown and Henno. Who understood that the set of large diffeomorphisms in ADS3 is the same symmetry group as a conformal group in 1+1 dimensions with a central charge given by the ADS radius in units of the Planck's constant. I've set the ADS radius to 1, so this formula looks weird, but really this should read LADS. If I want to put the LADS back, I should put it all over the place here. Which then says that the entanglement entropy for this interval is given by C over 3 log L over epsilon, which is the correct answer that was obtained long time ago by Wilczek and Larson in 2D CFTs, and later by Cardi and Calabresi, who showed how to get this by computing correlation functions of twist operators. Okay, so this is the field theory answer, and this simple geodesic formula reproduces that field theory answer. Okay. So that was the first simple check that the Ryuta and Nagi proposal does work in ADS CFT. So I gave you all the sort of conceptual reasons why it should work yesterday, but this is really the bottom line. It matches what you expect in field theory. So we could do some more examples, but I want to mention a couple of things. So let's do one interesting example, which is also simple, but has some interesting physics in it. So again, we'll do 2D CFT. We'll do it on S1 times R, and we'll take the state to be the thermal state. We are free to do this. It's just a thermal state on the cylinder, which we said we could take any state we want. I just want to do it in a mixed state to see that you can show that you can, and you can get the answer that's interesting. Okay, so what can we say about this guy? And we'll take, again, the region will be an interval. On the circle, where phi will take values from minus phi 0 over 2 to phi 0 over 2. Let me take it from phi 0 to plus minus phi 0 to plus phi 0 to avoid some factors of 2. Okay, so basically we have our field theory on a circle, and A is this arc of the circle. And we are at finite temperature, which means that the dual geometry, when I draw the bulk spacetime, is going to be a black hole spacetime. And you can write down the metric. Things are a bit more different in 1+1 dimensions than in higher dimensions, but it nevertheless is true that, like in the ADS-Schwarzschild black hole, we'll now have a slightly different black hole. It's called the BTZ black hole because they're in lower dimensions. Maybe this point is worth emphasizing. So in flat space, black holes exist in dimensions 4 and higher. The Schwarzschild black hole exists in 4 space-time dimensions. There is no analogous black hole in 3-dimensional Minkowski space. And the intuitive reason is obvious. In 4-dimensional Minkowski space, the Newtonian potential of a point particle falls off like 1 over r. So if I put a point particle, it has some mass, and its Newtonian potential fall off dies off at infinity. If you try to compute the Newtonian potential of a point particle in 3 dimensions in flat space, it grows logarithmically. Just solve the Laplace equation in 2 dimensions. The Newtonian potential grows logarithmically, which means that the effect of a point particle is felt very non-locally at infinity. What it wants to do is it wants to sort of destroy the asymptotics of flat space. So there are no black hole solutions because of this, which are asymptotically Minkowski in a suitable sense in 3 dimensions. But ADS has a asymptotics where the space, which is space, grows in volume as you go towards infinity. So there is room for a point particle to sort of make a deformation without spoiling asymptotics. So black holes exist in 3 dimensions in asymptotically anti-de Sitter spacetime, in contrast to asymptotically Minkowski spacetime. And again, you need this. You need this because I can take a 2-dimensional field theory and I can study it at finite temperature in 1+1 dimensions. And if ADS black holes didn't exist, I would be stuffed. So you need some story to say. And these black holes were found again much before ADS-CFT. This black hole is called the BTZ black hole, after Bagnados, Teitelbaum, and Zanelli, who found this black hole solution in 91. But there's a metric. You can write this down. It's actually intuitively simple, but I'll just say I'll just write the metric and leave it as that. It's easy to see where this metric comes from and so on and so forth, but let's not go there. So the temperature of the black hole is given in terms of this one parameter, r plus over 2 pi. So it's a very similar formula to what we had the other day. We had r plus over pi for 4-dimensional ADS-5 black holes. It's 1 over 2 pi for 3-dimensional solutions. And if I draw constant t sections, respecting this spherical symmetry, circular symmetry of the boundary, then you can basically understand the solution as the boundary living as r goes to infinity, which is the edge of this Poincare disk. Phi is the coordinate that parameterizes the angle, and there's a horizon at r equals r plus. And the interior of the black hole is the inside region. So the topology of so this is the first case where there's non-trivial topology, because since there's a black hole here, if I draw the Poincare disk, there's a hole eaten out of the Poincare disk by the black hole. Okay, I mean, strictly speaking, if you draw the Penrose diagram, and if you think of this Einstein-Rosen bridge picture I told you about yesterday, what you really have is two such Poincare disks with this wormhole starting out here connecting to the other asymptotic region. Okay, so the wormhole picture looks like this, but I'm just drawing one boundary and one so this is the wormhole slice, but I'm just drawing the sort of top half of the wormhole slice. I'm just cutting it off up there. Okay. So that's the solution. And there's another way to think about the solution. The Euclidean solution if I just replace r by r plus cosh rho, then up to an overall factor of r plus, you get this geometry. You may recall from the very beginning, I wrote down metric on global ADS in these row first. It was this metric, except that the cosh rho was in front of time and the sinh rho was in front of the space coordinates. If you go back to your notes from the beginning. So this space-time is just global Euclidean ADS3 has metric. This is BTZ. Let's put E for Euclidean, ds squared E ADS3 is cosh squared rho d tau squared plus d rho squared. Let me keep calling it TE. That is, to go from this solution to this solution, I just have to swap the meaning of Euclidean time and Euclidean angle because these metrics are the same. They're identical metrics up to an identification of what you mean by time and what you mean by space. Why is this? The Euclidean black hole has boundary S1 parameterized by angle phi times S1 parameterized by angle TE. Phi is periodic with period 2 pi. TE is periodic with P at beta. If you go back to my discussion from yesterday, I've given you the Euclidean geometry, which is a circle to the circle or a 2 torus. And you're supposed to fill in this 2 torus to find an ADS3 geometry. We had yesterday the example in higher dimensions where we had a circle times an S3. So if you go down in dimension, the S3 becomes an S1, just a circle of the angle. So how do you fill in a 2 torus? Well, depending on which part of the world you're in, it's either a donut or a bagel. So I have a 2 torus, and I have a filled 2 torus where I have one circle that goes out this way and another circle that goes out this way. Right? So this circle is contractible. This circle in this presentation is not contractible. But it is a Euclidean manifold, and I can choose to slice it different ways and call different things space and time, and I can swap between these two. Okay? Is that clear? Yeah? So the analog of our transition, the transition between black hole phase the phase transition between the black hole phase and the ADS phase. And thermal ADS happens at R plus equals 1, or really R plus over L ADS equals 1. Same point in parameter space as yesterday. Except that the BTZ black holes always have positive specific heat. So in higher dimensions, we saw that the Schwarzschild ADS black hole didn't exist for all temperatures. It only existed above a critical temperature. And there were solutions also with negative. There's only one solution branch here, and that solution branch also has positive specific heat. But nevertheless, we can run through the argument we had yesterday about the phase transition, and the phase transition happens here as well. Okay? So keep this in mind, because I want to try now to find entanglement entropy here in the high temperature phase. So again, use the fact that d by dt is killing and orthogonal to spatial sections to solve for GD6. In the R5 plane, can again pick some coordinates psi and try to work out the geodesic equation. Actually, it's nicer in this case. You can write an explicit formula. So let me write the formula. You can write for R of phi itself. Okay, I solve for the geodesics and then parameterize them as a curve in the R5 plane by eliminating C. Okay? So you can do that. I want to do this because I want to show you what these curves look like. And you can compute their length, etc., etc. And I'll write the answer in terms of the CFT answer. And this is okay, where R infinity is 1 over epsilon from before. Just want to use slightly different variables. So that's the naive answer you get. I'm going to write another formula in a second, so let me leave some space here. Because there's going to be this thing to jump, and the reason is the following. So let me start with small intervals on the boundary. Let me take a small interval like somewhere here. It has some, the curve which I plot, this curve, if I plot it in this R5 plane, looks something like this. It's distorted because it's sort of being pushed away by the black hole. And which is also easy to understand. So really, again, we're trying to solve for some soap bubble problem in a gravitational potential. The gravitational potential in ADS is very large near the boundary because the space is growing fast. And so the minimal surface, as I said before, wants to not go perpendicularly away from the boundary and then close off somewhere. If you were just doing this in ADS. But now there's a black hole here which is also providing a gravitational potential. So it's repelling the soap bubble because the soap bubble doesn't really want to go sit by the black hole and pay an energy penalty by being there. So it gets little bit distorted in that domain. So there's some interplay, and that's what this solution is telling you, that the geodesics are slightly different from what they would be in the same for the same domain in ADS. But what happens if I go halfway across the boundary? Well, it sort of wants to go out like this. And then comes back that way. But there's clearly another solution by spherical symmetry where it goes back down the other way. So let me talk about one more region. Let me make the region even bigger than halfway around the circle. Okay, so I'm going to anchor my origin is here. So phi 01 was here, phi 02 is here, phi 03 is, I guess, minus, minus, minus. Now we have two choices. This curve can either stay on this side of the black hole, or it can go back behind on the other side. Yes? In fact, there's a corresponding version of this orange curve too, which comes back behind this side. Okay. Now, which of these two blue curves is the right answer? Let me draw the blue curves now explicitly, because that's the only one I want to discuss. Which of these is the right answer for the entanglement entropy of this large region? You have two choices now. Which one should we pick? Anyone? Why? They both are geodesics. They both have zero extrinsic curvature.
As we have drawn it, we can only consider the topologically trivial one, right? Which one is homotopic to the boundary region?
That's right. So we have, the question is not one of homotopy, but one of homology. But yes, so we have to pick the one that is homologous to the boundary, the one that's retractable to the boundary correctly. This one, the one below, doesn't retract correctly to this region because it gets stuck on the black hole. This disk has been removed from my space-time. So the one in the mid, the one that's below below here, when I try to pull it back towards my region is the one up here. I don't get it back. Okay. This one, on the other hand, allows me to fill out this region, and so it's allowed so let me call these curves, let me not use the word gamma, let me call this geodesic S2 and this S1. So S1 is correct because it's homologous to the region. S2 is not. But you can cure S2. You can make S2 homologous to the region if you do the right thing. Let me draw one more picture. What about this guy? What about S2 plus H? The union of these two curves. These two curves, if they are the extremal surface, the common boundary of the extremal surface, there's a space-like region whose only boundaries are the extremal surface and the region A. So these two surfaces, the small curve plus the horizon, is actually homologous. So if it was just S2, when I try to push it back towards the boundary, it gets stuck on the horizon. But if it's S2 union the horizon, then I don't care because I can push it back. The horizon is also part of, I have to push out everything. And I push them out, and so bubble happily goes back to the boundary. Right? So we have this guy and this guy, which are both satisfying all the requirements. And it's useful to know, for the same reason as we had in the ER equals EPR story, the horizon is also a minimal surface. By itself. So it also solves the field equations you want it to solve. So, you tell me. Yes? Can I? This disk is cut out of this disk. The center is not there. What are the boundaries of S1 union S2? This was S2, this was S1, sorry. If I try to pull them inward, they get stuck on the horizon. If I try to push them outward, they still get stuck on the horizon. Because S1 by itself is homologous to A, S2 isn't. Yeah? So you can't, so there's nothing else. You can convince yourself by drawing the pictures yourself. So these are the only two choices. And now there's a question. We've solved the field equations. We've solved the homology constraint, but we have two solutions. Okay. So the entanglement entropy is given by not this or some average thereof or some weighted average thereof. It's really given by one of them, whichever happens to be the smallest area one. Okay? And so this is the answer for S1. The answer for S2 plus the horizon is similar, which you can get it by just swapping phi to pi minus phi. And accounting, so this is the answer for the S2 itself, and this is the answer for the horizon. The area of the horizon is just a circle of radius r plus. So if you translate everything, you get is a perimeter of a circle of a size radius r plus. And now it's a matter of comparison. You just have to minimize these two functions. So there exists some phi critical below which S1 dominates and above which S2 plus H dominates. Dominates meaning it minimizes this expression. You can work out what phi 0 critical is. It's some simple, you just have to equate those two expressions. So here's the answer. It's a function of the horizon size. So, strangely enough, this formula has existed in the literature for quite a while, but this understanding didn't come about till a few years ago when few of us with Eric and others understood that this phase transition has to happen. And this has a nice interpretation when for phi bigger than phi critical, we can convince ourselves that something nice, interesting happens, because since S2 is the extremal surface relevant for a complement, because if this guy is A, this little guy here is a complement. We're still talking about one copy of the field theory. What this is saying is that entanglement entropy of A is the sum of the entanglement entropy of a complement and the entanglement entropy of the entropy of the full boundary, which is the entropy of the black hole. Or in other words, you will recognize that what this says is that the Araki-Lieb inequality is saturated I wrote on the Araki-Lieb inequality yesterday, which says that SA minus SA complement is bounded from above by the total entropy of the system. So this is another Largen phenomenon. I'll call it a phase transition in quotes because it's a transition in the behavior of surfaces or how the entanglement pattern in the field theory is encoded in the degrees of freedom. Okay. Just as there was a thermal phase transition, this is some kind of entanglement phase transition in the system. The same underlying physics dominates. And there's one other place where this happens, which I will explain in a second, once I check whether people are happy with this discussion. Questions? Yes. So there's one way to say it. So because we have a black hole, A union A complement, which is the one boundary of the CFT, is in a thermal state. So it has non-zero entropy. Right? And the presence of the black hole forces with the homology constraint. See, the two things operating here. One is the black hole itself, but the second is the homology constraint from the point of view of geometry. That's what forces us not to take the small region. Okay? Now, so those two things conspire to tell us that there is non-zero right-hand side to this inequality. So, and the saturation happens because the thing that's minimizing the entanglement, determining the entanglement entropy, is a disconnected surface. With a single connected surface, either S2 or S1, that wouldn't happen. There's a better way to say this, which was pointed out to us by various people, and Eric was the first to realize this, which is that SA is entanglement of stuff in A with everything outside A. Right? That's what entanglement entropy means. If you think of bell pairs, it's all the pairs all the qubits that are in A and all their partners that are somewhere else. But since we're in a mixed state, A union A complement itself is not pure, but A union A complement, which I'll think of as the right CFT, union the left CFT is pure. In this ER equals EPR, in this wormhole sense, this is the right theory, this is the left theory. There's an EPR bridge that has entangled the right and left theories, and what I'm asking for is entanglement of some piece of the right theory. But clearly that piece of the right theory is entangled with both the stuff that's in the right theory itself, they complement here, and the stuff that's in the left theory. Because I've set up the thermal density matrix, I've set up thermal correlations, and those thermal correlations are set up between everything here and everything here. What this is saying is that generically there's no way to sort of tell apart how stuff in A is entangled with just a complement and how it's entangled with the purifier of the thermal state. But in this domain, when the Araki Lieb is saturated, there is some separation. There's a clean separation of what's happening.
Here we are studying the thermal theory on S1 cross R. We could have probably tried to study a thermal theory on R1, 1.
Yeah.
In that case, would we have the sort of...
The phase transition won't happen because it's the presence of the circle, the finiteness, that's what matters. The transition happens but at infinite distance, so you don't see it, it disappears. Just as the Hawking-Page transition doesn't happen on the plane.
So is this an equivalent of Hawking-Page phase transition?
It's morally speaking similar. It has the same underlying physics, the same reason why it happens.
But then where does temperature appear in this?
The temperature appears because of R plus. The transition point cared about what temperature I was at. Yeah, so the transition point which I just erased happened at some funny function of cotangent inverse of R function of R plus. So I'm only measuring the temperature because I fixed the size of the circle. What really matters is the temperature measured units of the circle size. So R plus was measured in the circle size units. So it is like the Hawking-Page transition, because make it bigger, the temperature at which it will happen will scale appropriately. So if you make it, if you make the system non-compact, if you put back the dimensions and rescale the circle to be the line, the transition will happen at infinite temperature, so you won't see it. Okay, but that's what's happening. There's some kind of, what holography is trying to tell us is that there's some kind of localization of what is entangled with what. It's in spatial localization, which is funny from an entanglement point of view. So there are other examples of this phenomenon, which I'll just draw for you. I'll just call them entanglement transitions. And let's do this for, I don't know, we could do this for a, let's do it for CFT on R11, but now for A being two disjoint intervals. So I have an interval here and I have an interval here. And we could have this surface, which is two disconnected surfaces. They're homologous to A because this guy retracts to A1, this guy retracts to A2 correctly. But there's another surface which also does the job. Okay. And you can ask which one dominates. Again, it's a question of finding their lengths. And you see that if these two intervals are far enough apart, you pay a large price to construct a dome that straddles them. So the green surface doesn't dominate if these two things are very far apart, but it does dominate if they're close enough together. So as a function of this separation, let's call it chi. Oh, my chi looks like an X. So for large chi, we have disconnected surfaces. For small chi, we have connected surface, single surface. And so people understood this. Matt Hedrick understood this by thinking about how conformal field theory, how the conformal field theory calculation works, and then later Tom Faulkner and Tom Hartman showed independently, one in gravity and the other in conformal field theory, that these kind of transitions do happen if you work with conformal field theories with large central charge. So the gravitational prediction can also be tested by just studying conformal field theory calculation of these guys, by working in the large central charge limit. Okay, so that was, I think that's all I want to say about entanglement entropy for now. Do people have questions? Okay, so let me say a couple of things about other applications of area CFT. In trying to understand properties of strongly coupled field theories. So what we've seen in all of our discussion is that corresponding to every field theory question, there is some geometric problem and while the geometric problem may be hard to solve, it's nevertheless a geometric problem that's solved by solving classical equations in some space-time. So all of the quantum dynamics, which is inherent in asking the CFT quantum field theory question, gets distilled into a simpler geometric question in the gravitational context. So this makes this correspondence very powerful to understand, to ask questions about actual dynamics or time-dependent situations. Where it's not so much that we don't understand how to formulate these problems in quantum field theory. We certainly can formulate questions involving non-trivial time dependence in quantum field theory, and we know how to sort of try to address those formally, but the computation of them at strong coupling is prohibitively hard. So for some class of questions, ADS-CFT is just the right opportunity where you can sort of ask those questions and at least learn clear qualitative picture of what's going on. And in some cases, that qualitative picture is much better than that. It's actually a quantitative story of what's going on. So we could ask questions like, if you excite a system, if you take a system away from thermal equilibrium, how quickly does it return? How quickly does rethermalization occur? What are the time scales for various relaxations, and you can ask also, are there, while these are dynamical questions, you can also ask, are there non-trivial quantum phases of matter at finite density, etc., etc. You know, what dominates where, etc., etc. We saw already that we can have non-trivial phase transitions. So you could sort of start asking these type of questions in ADS-CFT by just asking corresponding questions in gravity. And I'll phrase this, I mean, the story is of what ADS-CFT has been used for is long, rich, and vast. So ADS-CFT has been used over the last decade and a half to study QCD dynamics, and evolution of quark gluon plasma. This was the first application, if you like. It was used subsequently to understand phase structure of many body system. So people figured out how to model things that look like superfluids, things that resemble properties of non-Fermi liquids. Incoherent metals. And in all these cases, you're not really studying the true theory that experimentalists are trying to study. I mean, this is some material in the lab that people do study and try to extract the properties of. This is QCD. This is not N equals for Young-Mills. But in all cases, there's a sort of the philosophy here is you try to write down some effective field theory that captures the right kind of questions you want to ask, and ask whether that effective field theory can be studied holographically using ADS-CFT, and whether you can then learn properties that are relevant for these guys. If you see qualitative physics, see in the experiment, you at least have some this phenomenological modeling of what's going on. And last but not least, there's a lot of excitement in trying to understand dynamics of entanglement, time evolution of entanglement. And the question that's most fascinating is perhaps a sort of general lesson that comes out of this analysis in many cases is, are there fundamental bounds on quantum processes? Could we say that some quantity has to be bounded from some domain? It can't be different from something, maybe due to some uncertainty principle or due to some other profound reason? Or can you say that some phenomenon, in quantum dynamics, can never happen faster than some value, etc., etc.? Okay. So this is a question that's very actively being researched. And I have only half an hour, so I'll give you a sort of sketch of what's going on, what people are interested in here, and what was done. So my strategy is going to be to try to tell you a series of gravitational experiments that have been carried out, which means you either solve a set of PDEs on a computer or you solve some properties of some metric and figure out what's going on. And I'm going to translate them into properties of which allude to what these things are saying. So here's the first statement. So let's start with thermalization. And here we can ask two questions. We can ask a question which says, look, I'll start with global thermal equilibrium. Start with initial temperature T. And excite the system and watch it settle back down. Can you give me rates for settling back down? So this question was answered way back when, in the previous millennium, in late 90s, soon after ADS-CFT, because people realized that the right way to phrase this question is a gravitational problem is to start with a black hole, which corresponds to this thermal equilibrated state at temperature Ti, and excite it. So we can go back to our picture we had before. And so we have a Schwarzschild radius black hole or some other black hole that sort of describes our equilibrium scenario. And then excitations means you throw stuff into the black hole. Right? Because I'm throwing an energy into my system, and all energy I throw into a gravitational system gravitates, and black holes are perfect because they want to absorb everything that you throw at them. But black holes do something nice, that if you throw energy at them, the horizon of the black hole behaves like an effective membrane. You know, stuff falls on the horizon. It falls behind, it goes behind your causal contact. You can't get signals back from it, but it leaves behind an imprint on this horizon. So I didn't sit through the cosmology lectures, but just as in inflation, stuff re-entering our horizon leaves behind signals on the universe. Stuff going through the horizon leaves behind signals on, imprints on the horizon. And there's a decay rate for stuff falling through, because this is more like this horizon is a one-way membrane, so stuff is disappearing from our access. So we are losing information. And the energy we throw in ends up sort of eventually growing the horizon a little bit. The horizon sort of comes out. The amount by which the horizon comes out corresponds to how much energy you threw in. And these decay rates can be computed by solving a classical problem. By solving the wave equation for fields in an open domain, because if I draw that picture by drawing the boundary here and the horizon here, if I have some waves that I'm throwing into the black hole, this is a gravitational potential well, like any potential well, waves scatter back through that potential well. Some things fall through, some things get reflected back. But I have open boundary conditions here. So it's like a quantum mechanical scattering in a potential with open boundary conditions. I'm not accessing part of the potential that's going out this way. So you don't get, if you solve open quantum problems, you don't, if you solve the eigenvalue, if you solve for the spectrum, you won't get, because of the open boundary conditions, you won't get real eigenvalues for the energy. You'll get complex eigenvalues because stuff is disappearing. Okay? So let's call it eigenvalues or eigenenergies for the scattering states. And in the black hole context, these are called quasi-normal modes. In general, for any open problem, the distinction from usual quantum mechanics scattering is that if you have real eigenvalues, you have normal modes, which are propagating degrees of freedom. But if you have damping in a system, you have quasi-normal modes. And say you have our favorite black hole that we studied the other day. Or let's even take the BTZ black hole we studied a short while ago. We can scatter a scalar field can scatter it off the black hole, which means you solve the Klein-Gordon equation by more decomposing the scalar into some frequency modes and momenta which are on the circle and some radial wave function. And the quasi-normal modes are defined by the eigenvalue problem. For this chi of r, so you solve but to get eigenfrequencies omega such that the boundary conditions are chi of r is normalizable as r goes to infinity, and chi of r is purely infalling into the horizon. Okay, so in other words, you solve this problem by dumping energy in, and then you chop off. You look for only the solutions that are going into the black hole. There's no backscattering. And so you have a discrete set of frequencies with complex eigenvalues, which tell you properties of this black hole, which in turn, translated through ADS-CFT, tell you properties of this thermal state of the field theory. Okay? So in this BTZ case, you can actually solve the wave equation exactly. It's an analytic problem. There's this chi of r can be solved in terms of hypergeometric functions. If you write down the wave equation, you can do it in, depending on how good your memory is about hypergeometric functions, you can do it in a couple of minutes or a couple of hours. You can find the eigenfrequencies. It's all very straightforward. In higher dimensions, you can do the same problem. The wave equation is a bit more messy, but you can solve it numerically and understand what the frequencies are. So people have done this, and one lesson that came out of this is the following. For gravitational modes, so let me show you a picture. So the frequencies, the eigenfrequencies, are complex, and since I have a exponential damping, I have an oscillatory with a minus I. If omega is complex, then this has an oscillatory piece and a damping piece. Yeah? So stability requires that omega I, as written with this convention, is positive, because otherwise, if omega I is negative, I don't have exponential damping, I have exponential growth. If I throw energy at the system, it runs away from its equilibrium. So if you think of the complex frequency plane, you want all these eigen energies to be in the lower half plane, which is what this convention means. Okay? And you indeed find this for most of the black holes. You find that you have a discrete spacing of eigen energies. There's infinitely many of them that have some discrete spacing. So in the BTC case, if I remember correctly, there's some okay, let me not write an answer that I don't get right, but it's basically you can work out the answer that the frequency is proportional to the black hole temperature, and it's actually harmonic oscillator spaced with the imaginary piece is a harmonic oscillator space set by temperature. So it's a very nice spectrum because of a very simple geometry. Okay, so that's the answer you get there. But if you solve more complicated problems, you can solve, of course, we just pick some scalar field. So this is telling us the behavior of some scalar operator in the quantum field theory by ADS-CFT. But you could ask what happens to for other operators like conserved currents, which are special because they have like energy momentum tensor. And there you find, so you have to solve a more complicated problem because the energy momentum tensor couples to gravitons. So you have to do graviton scattering of the black hole. It's possible, you can do it. It's just a messier wave equation. Although a part of it looks like the scalar problem. But what you find is something a bit more interesting. So you find again some series of modes that are sort of in the complex plane. But you also find in the scalar problem, all modes are separated from the real axis by some distance set by the temperature. Okay? But in the black hole case, when you scatter conserved particles, conserved currents, or scatter gravitons, there are what I would call light quasi-normal modes, whose frequencies are vanishingly small for small momenta. So you have some omega as a function of the black hole parameters and some momenta, but they go to 0. There's a handful of modes which have this property. What this means is that there's a low energy sector of the theory which is the small momentum sector, which you can isolate by sort of forgetting about all these other modes and just focusing on this one mode. So it's a bit like symmetry breaking phenomenon, where you have global symmetries being broken. You have lots of excitations in the system, but you only keep the Goldstone modes, and you try to study the low energy physics by looking at the Goldstone modes. So there's a theory of there's a theory of these Goldstone modes, which one can show after some work is actually the theory of hydrodynamics. And what's interesting about this is that what it says is that the black hole behaves at late times and long distances like a fluid with material properties and one of these material properties is a viscosity, the shear viscosity, which tells you how much two fluid layers shear past each other. If you sort of try to shear the fluid, if you try to shear a fluid layer past another fluid layer, how fast how much friction there is. That's what the shear viscosity measures. Now, the reason this became very interesting is people did this computation. This was done in 2001 by Polycostros and Starinets, and they found that the shear viscosity could be expressed as some number. Now this guy has dimensions, and the right way to compare across different materials is to normalize the shear viscosity to the entropy density. So eta is the shear viscosity and S is the entropy density. It's the entropy per unit volume. And I want to compare properties of shear viscosity of this material that is modeled by a ADS black hole with shear viscosity of, say, water. I can't just compare the two numbers because the numbers don't mean anything, but if I can, the dimension full, but I can compare them by normalizing them with respect to some in fiducial scale, which is the entropy density. And you find that for black holes, you get an answer which is 1/4 pi. In fact, if I put dimensions right, you get h bar over 4 pi kb. And what they noticed was that this number is anomalously small, is much smaller than anything that you would see in any other material. So the closest that comes to this material is liquid helium, at its superfluid point has eta over s, which is about factor of 10 larger than this value of h bar over 4 pi kb. I mean, water is just way off the charts compared to these numbers, by a factor of 100 or so. If you actually want numbers, eta itself is about 1 for water in units called Poisson, whereas for this black hole plasma, it's 10 to the 14. So if you just compare eta, you'd say the black hole plasma behaves like a glass because it's glassy materials which have very high viscosity. But when normalized correctly, then that was a great intuition that these guys had, that you can compare them across materials without worrying about what units you're using, and you see that this shear viscosity is really the smallest you can hope to find in most materials that you know. So what was really sort of great about this analysis was that this analysis was done for an n equals 4 plasma by studying ADS5 black holes. And this was around the time people were studying the quark-gluon plasma by colliding heavy atoms to make a soup of quarks and gluons. So there was an ADS-CFT calculation, but there's also the quark-gluon plasma which was being studied at RIC, also was behaving as a fluid, local thermalization, with an eta over s, which is almost similar in ballpark. I think the best results I have seen are about maybe a factor of 2 of this number, and there's still a lot of interest in trying to understand this quantity from LHC runs of quark-gluon plasmas. LHC just started colliding heavy ions yesterday, again after in the second run. And so what this suggests is that there is a strong coupling dynamics of QCD or holographic theories or holographic quantum field theories, which underlies the fact that the viscosities is so low. Okay. So people have called this quark-gluon plasma a nearly ideal fluid. An ideal fluid is one which is not viscous, A nearly ideal fluid is one which is not viscous is viscous but by a small amount. And the best handle one has at trying to understand why is it that QCD behaves this way qualitatively comes from complementary analysis of gravitational systems. Okay? So this is one of the examples of these fundamental bounds that people have tried to understand over the last 10-15 years. Is it that when you have strongly coupled dynamics of quantum field theories, do things like viscosities satisfy some lower bound? So because people have then gone on to conjecture that eta over s is bounded from below by 1/4 pi. It's the bound, it's usually called the Cove-Thun-Son-Starinates bound. Is this fundamental? Can one derive this from some first principles? So there have been lots of explorations of where this bound could come from, so on and so forth. In the same spirit, there's a much more interesting bound which has been discovered in the last half a year or so, which I will mention and then stop, which is these days called the chaos bound, or what I like to think of as a scrambling bound. Which says that the rate of rethermalization of a chaotic system is governed by a Lyapunov exponent rate of, let me say, onset of rethermalization and this guy is bounded by something of order t with a factor of 2 pi. Okay, so this was again obtained by studying dynamics of stuff in black hole backgrounds. This bound was proposed by Maldacena, Schenker, and Stanford, and it sort of seems to imply this bound, and perhaps is a bit more robust. But this is the kind of questions that people are interested. Are there fundamental bounds that one can learn by studying dynamics of black holes, studying dynamics of gravity, studying dynamics of strings, that tell us that quantum processes can't happen beyond at some rate, beyond some rate? And the nice thing about ADS-CFT is that it's very easy to study the gravitational side to come up with these bounds in the first place, because many of the calculations that are done, either solving wave equations or doing the calculations that were done by Schenker and Stanford and so on in this context, they're very straightforward gravitational calculations. They're computationally involved, but they're nowhere as involved as trying to do computations in a strongly coupled quantum field theory. And once you have the answers, you can then go back and try to ask whether there's some fundamental principles of quantum dynamics that tells you what this is. And that's the question that I don't understand. And that's where I think ADS-CFT has the greatest promise of trying to teach us lessons about quantum field theory. Okay? So I think there's a lot more to say about what ADS-CFT can and cannot do, but I hope I've given you a flavor of the kind of field theory questions that you might hope to answer. I have not at all focused on an aspect of ADS-CFT that I find personally quite interesting, which is what does it teach us about quantum gravity, but that will be a topic for another time, another day. Let me stop here. Questions? No? All right, so let's go get lunch.